Hello everyone, welcome back to my YouTube channel. I hope you are enjoying my videos and at the same time learning from it. So today in this video we will be discussing about the spherical lenses. We'll also discuss about the types of the spherical lenses and image formation by spherical lenses, that is convex and concave. So let's start this video. So first of all, what is a lens? So a lens is a transparent refracting medium which has two surfaces, out of which one or both are curved. So a lens is nothing but a transparent medium through which light can be refracted, and it has two surfaces, and out of these two surfaces either one of the surface is curved or both the surfaces are curved. And depending on the shape of the lens, we have two types that we will discuss here. Basically there are more, but we will discuss only two types of lens, that is convex and concave. So let's start the video here. So you can see a lens is nothing but a transparent refracting medium bounded by two surfaces, at least one of which is a curved surface. At least means one at least is a curved surface, the other may be plane, or both the surfaces may be curved surfaces. So here we will discuss only about the two types of lenses, that is convex lens, or we also call it as the converging lens. We'll discuss this later, why we call it as converging lens, and concave lens or diverging lens. Convex is also called as biconvex. Why we call it as biconvex is simply because if you look at this diagram, this is a convex lens. So this convex lens has two surfaces, and here both the surfaces are curved outside. That means it is convex in nature and it has two surfaces. That's why we call it as biconvex, or simply we call it as convex lens. And the other name is converging lens. Similarly, here we have a concave lens. It also has two surfaces, and if you look at the surface is curved inside. That means it has concave nature. So we call it as a biconcave, or simply we call it as a concave lens, and the other name is a diverging lens. So a lens has two surfaces, one or both may be curved, and depending on the curvature we have here two types of lenses. One is convex, in which both the surfaces are curved outside or bulged outside, and concave, in which both the surfaces are curved inwards. So the difference between convex lens and a concave lens you can see is, for a convex lens the center is thicker, but for a concave lens the center is thinner. For a convex lens the edges are thinner, and for a concave lens the edges are thicker. Convex lens is a converging lens and concave lens is a diverging lens. So if they ask you the difference between a converging lens or a convex lens and diverging lens or a concave lens, then you can basically write 2 points here. Now let's discuss about the terms related with the lens. Okay, so let's discuss about the terms related with the lens. So the first term is optical center, which is represented by O. So what is an optical center? So it is the center of the lens. Whether it is a convex lens or a concave lens, the center of the lens we call it as the optical center. And if a ray of light passes through this optical center, it goes without any deviation. That means it will travel in the same straight line. So that is our optical center. The second term is center of curvature. So in the mirror also we have discussed about the center of curvature. So similarly here, the center of curvature is the center of the sphere of which the surface of the lens is a part. So we have two surfaces in a lens. If we extend that, then it forms a sphere. So the center of that sphere, of which the surfaces are just a part of it, is called as the center of curvature, represented by capital letter C. And here we will see in the diagram that for a lens we have two center of curvatures, C1 and C2, for the two surfaces. The third term that we have is the radius of curvature, which is represented by the letter R. So what is radius of curvature? It is the radius of the sphere of which the two surfaces are a part of it. And the principal axis, it is a straight line which passes through the center of curvatures of the lens. So these are some of the terms. We will discuss more terms related with the lens. Let's understand this in the diagram first of all. Okay, so let's look at these two diagrams. The first one is a convex mirror, and the second one convex lens, and the second one is a concave lens. So whether it is a convex lens or a concave lens, it has a center. So the center of the lens, we call it as the optical center. So for both the spherical lenses, its center point, we call it as the optical center. Now, the next thing, if we extend the two surfaces of convex lens as well as the concave lens, then we will get a sphere. For example, if we extend this first surface of this convex lens, then we will get a sphere like this. And similarly, if we extend the second surface, we will get another sphere here. So this sphere has its own center. So the center of this sphere, of which the two surfaces of the lens is just a part, is called as the center of curvature. For example, for this first surface, its center will be somewhere here. So this is the center of this sphere, of which this surface is just a part. So this center is called as the center of curvature for the first surface, and we represent it as C1, center of curvature for the first surface. Similarly, for the second surface, the sphere is formed on the left hand side here. So its center will be somewhere here. So this is the center of curvature for the second surface, so we will write it as C2. So center of curvature is the center of the lens, or center of the sphere, of which the surfaces of the lens are just part of it. Similarly, for a concave mirror, if we extend this first surface, then we will get a sphere on the left hand side. So the center of this sphere will be C1, and for the second surface, the sphere will be formed on the other side, and its center will be C2. So in both the cases, we have two center of curvature, C1 and C2. But see the difference. For convex lens, C1 is towards right and C2 is towards left, because this is for the first surface and this is for the second surface. But for a concave lens, C1 is on the left side and C2 is on the right side. The C1 is the center of curvature for the first sphere, which is formed, and this first surface is part of it, and C2 is the center of the second sphere, for which this second surface is a part of it. So there are two center of curvatures. Now radius of curvature is nothing but the distance from the center of curvature up to the surface or up to the sphere. For example, this distance is R2 here, and this distance from here to here, it is R1. So radius of curvature is the distance between the center of the curvature and the sphere, of which the surface is just a part of it. Similarly here, if we have to consider, then from here to here, this distance is R1, and similarly from here to here, this distance is R2. Alright, so we have two center of curvatures in case of lenses. For mirror, we have only one center of curvature, but for lens, we have two center of curvature, and similarly, we have two radius of curvatures. And the last one, principal axis. It is the straight line passing through the center of curvatures of the lenses. So there are two center of curvatures, C1 and C2. So if we draw a straight line passing through these 2 points, then this straight line, we call it as the principal axis. So for both concave lens and convex lens, if you draw a straight line passing through C1 and C2, then that straight line, we call it as the principal axis here. I hope these terms are clear. Let's discuss more terms related with the lens. So let's discuss the focus. First, principal focus. In case of a lens, we have two foci. So the first focus and the second focus, and its definition will be slightly different. So let's discuss it individually. So first, principal focus, which is represented by F1. For convex lens, the definition will be, it is a point on the principal axis such that rays emerging from it or starting from it after refraction through the lens becomes parallel with the principal axis. So it is a point which lies on the principal axis, and if the light rays emerge from this point and it passes through the lens, then after refraction it becomes parallel with the principal axis. But the same thing for a concave lens will be, it is a point on the principal axis such that rays parallel with the principal axis after refraction through the lens appears to come from that point. So the definition is slightly different. Let's understand it in this diagram. So if you look at this first lens, it is a convex lens, and this is the point on the principal axis, which is the first principal focus f1. So we have two rays emerging from this point f1. So as this ray passes through the lens, refraction will take place, and after refraction, these rays will become parallel with the principal axis like this. So now you can read the definition and try to understand. F1, which is the first principal focus, is a point on the principal focus such that rays emergent from it after refraction through the lens become parallel with the principal axis. So this is first principal focus for a convex lens. Now for a concave lens, you can see these are the incident rays which is parallel with the principal axis. And after refraction, it gets diverged. Diverged means it goes in different direction. That's why we call it as a diverging mirror, and this one we call it as a converging mirror. So this refracted rays goes in different direction. Now if we produce this refracted rays backwards, then it will appear as if these refracted rays are coming from the point f1. So let's draw this here. So if you produce this refracted ray backwards, then it will just intersect this point, which is the first principal focus f1 for a concave lens. So f1, first principal focus, is a point on the principal axis such that rays parallel to the principal axis after refraction through the lens appears to come from it. So this refracted rays appears as if it is coming from f1 here. So these two definitions are for the first principal focus for convex mirror and a concave mirror. Similarly, we will discuss about the second principal focus for convex mirror and concave mirror. Concave lens and the convex. Alright, so the definition for the second principal focus for convex lens and concave lens. So for convex lens, it is a point on the principal axis such that incident rays parallel to the principal axis after refraction through the lens passes through it. So as you can see in this diagram, we have convex lens and we have incident rays which is parallel with this principal axis. So as this ray passes through the lens, refraction will take place and this refracted ray will actually meet at the point f2. So if you draw these refracted rays, then these refracted rays will meet or intersect at the point f2. So this point is called as the second principal focus for a convex lens. So read the definition. It is a point on the principal axis such that incident rays parallel to the principal axis after refraction through the lens passes through it. That means this refracted rays will pass through this point f2. So this is the definition for second focus of convex lens. Now for a concave lens, it is a point on the principal axis such that rays traveling towards it after refraction through the lens becomes parallel with the principal axis. So here in the diagram you can see we have two incident rays which is going towards the point f2. So this f2 is a point on the principal axis such that incident rays going towards it after refraction through the lens. As the incident ray enters the lens, refraction will take place. These incident rays are going towards the point f2, and after refraction these rays will become parallel with the principal axis like this. So this point f2 is called as the second principal focus for a concave lens. Now the last term, focal length. So focal length is nothing but it is the distance between the focus and the optical center of the lens. Now since lens has two different foci, so there will be two different focal lengths. If the distance is from optical center to the first focus, then we call it as f1. Remember, focal length is represented with letter small f and focus is represented with f, capital F. So if the distance is between the optical center and the first focus, capital F1, then focal length will be f1. And if the distance is from optical center to the second principal focus, then we can write the focal length as f2. So there will be two focal lengths, f1 and f2, in case of a lens. So you just have to remember the definition. It is the distance between the optical center and the focus. Alright, now in order to do the image formation by a convex lens, first let's understand the rules. So using any of the two rules, we can form the image by a convex lens. So we'll do separately for convex lens and then we'll do it for a concave lens. So the first rule, it says that if the incident ray is parallel with the principal axis, then the refracted ray passes through the second focus f2. Look at this diagram here. We have a convex lens. This is the incident ray. This incident ray is parallel with our principal axis. So the rule says if the incident ray is parallel with this principal axis, then after refraction, the refracted ray must pass through the second focus. So this is our rule number 1. Now rule number 2, it says that if the incident ray is passing through the first focus f1, then the refracted ray becomes parallel with the principal axis. So here you can see the diagram. Our incident ray here is passing through the first focus f1. Remember, I have told you that there are two principal focus or foci for a convex lens and a concave lens. So this one is the first principal focus. This one here is the second principal focus. So in the first rule, incident ray was parallel, refracted ray was passing through the second focus. Here in rule number 2, incident ray is passing through the first focus, and after refraction, the refracted ray becomes parallel with our principal axis. Now rule number 3, if the incident ray passes through the optical center, then it goes without any deviation. That means it will travel in the same straight line. For that, the incident ray must pass through the optical center. Optical center is the center of the lens. So if an incident ray falls on the optical center, then it goes without any deviation. It will travel in the same straight line. So these are the 3 rules with the help of which we can do image formation by a lens. So let's discuss image formation by a convex lens. Okay, so let's discuss the first image formation by a convex lens. So in the first case, we are given an object which is kept at infinity. So I have mentioned this before also when we were discussing about image formation by mirrors, that whenever an object is kept at infinity, then the incident rays are always parallel to the principal axis. So here also, since our object is at infinity, the incident rays are parallel with our principal axis. So this line is the principal axis here. So these rays are parallel with this principal axis. So we have to find out the position of the image, that means where will be the image formed, size of the image and nature of the image. So here we will be using the first rule, which says that if the incident ray is parallel with the principal axis, then the refracted ray will pass through the second focus. So let's draw the refracted rays here. So all these incident rays, after passing through the lens, that is after refraction, will pass through this point f2, which is called as the second principal focus here. So we have done this before also when we were discussing about mirrors. So I don't think it will be much difficult for you. You just have to remember the rules. That is very simple. So here we have used the first rule only. If the incident ray is parallel with the principal axis, then refracted ray will pass through the second focus. So this point here is f2. And wherever the refracted rays intersects, the image will be formed at that particular point. So here all these refracted rays are intersecting at the same point, that is f2. So the image will be formed at the point f2. And since f2 is a point, here we can write position of the image. First of all, image is formed at the second principal focus, that is f2. Now if you look at the size of the image, it is a point size image or highly diminished, you can write down. So you can write down point size image, or you can also write down highly diminished. That means the size of the image will be very small as compared to the size of the object. So highly diminished. Now the next thing is nature of the image. For this you have to remember that convex mirror always forms real and inverted image. So here we cannot see that the image is inverted. In other cases we will try and find out that or see that the image will be real and inverted. So here for this time being we will write real and inverted. Real images are always inverted. So this is the first case. This is not so important. So when our object is at infinity, image will be formed at f2. It will be a point size image, or you can write highly diminished, and the image formed will be real and inverted. So this is the first. Okay, so this is the second case where our object is kept beyond twice of f1. So with the help of the scale, you can measure accurately and draw the diagrams properly. So we have a convex lens having optical center O. This distance here is f1. Now take the same exact distance, double of it will be twice of f1. So here we are keeping an object which is beyond twice of f1. So similarly on the right hand side also, this is f2, double of that will be twice of f2. So here we have to find out position, size and nature of the image when our object is beyond twice of f1. So here again we will be using two rules. The first rule, or the first incident ray that we will take, is parallel to the principal axis, and the second incident ray we will take passing through the optical center. So using the rules, we know that if our incident ray is parallel with the principal axis, then the rule says the refracted ray must pass through the second focus. So if you draw the refracted ray here, then the refracted ray must pass through the second focus f2. So you simply draw the refracted ray passing through the point f2 like this. So this is using rule number 1, which says if the incident ray is parallel with the principal axis, the refracted ray will pass through the second focus here. Now the next rule that we are using is, or the next incident ray we are taking is passing to the optical center. And the rule says that if the incident ray is passing through the optical center, then it goes without any deviation. That means it will continue to travel in the same straight line. So the refracted ray here will travel in the same straight line. So we have two refracted rays here. This one passing through f2 and this one going in the same straight line. So the two refracted rays are intersecting at this particular point. So wherever the refracted rays intersect, what we have to do? We just have to drop a perpendicular on the principal axis like this, and this will be the image of the object here, right? So we will see that the image formed here will be inverted and it is real. Why real? Because this image is formed due to actual intersection of this refracted rays. So let's write this now. Position of the image, as you can see, this image is formed between f2 and twice of f2. Between these 2 points, our image lies. So position of the image will be between f2 and twice of f2. Size of the image, as you can see, the size will be diminished. It is smaller as compared to the size of the object. And nature of the image, as I have said, it is inverted, and inverted images are always real. So it is real and inverted. So if you know the rules, then image formation is very easy. So here we have used two rules. One, parallel to the principal axis, passes through the second focus. Second, one passing to the optical center, goes without any deviation. Wherever the rays intersect, just drop a perpendicular on the principal axis. That will be the image of the given object. Okay, so this is case number 3, where our object is exactly at twice of f1. So here we need to keep the object at twice of f1. So you can see we have an object at this point which is twice of f1. So we need to find out the position, size and nature of the image formed in this case. So again we'll use the same rules. The first rule, or the first incident ray that we are taking here, is the incident ray which is parallel with our principal axis. Now according to the rule, if the incident ray is parallel with the principal axis, then after refraction it must pass through the second focus. So remember the rules. That will be easy for you to draw the ray diagram. You just have to learn the rules. So if the incident ray is parallel with the principal axis, the refracted ray passes through the second focus. And the second incident ray we are taking is passing to the optical center. And the rule says if the incident ray passes through the optical center, then it goes without any deviation. That means it will travel in the same straight line. So this will be the direction of the refracted ray. Now again, we have the two refracted rays here, and these two refracted rays are intersecting at this point. So wherever the refracted rays intersect, we'll get our image. So what you have to do, you just have to drop a perpendicular on the principal axis like this. So this will be the image of the given object, right? So since the image is formed due to actual intersection of the refracted rays, this image will be real and inverted. Now let's write the position, size and nature. Position, you can see it is formed exactly at twice of f2. So when the object is at twice f1, image will be at twice of f2. Now since these two are at the same distances from the optical center, the size of the image and the size of the object will be equal or same. So you can write size of the image same as the object, or equal in size you can write. So nature of the image will be real and inverted. So if you know the rules, it does not take much time. Okay, so this is case number 3. Let's do the next case now. Okay, our next case is object between f1 and twice f1. So here we have to keep an object between the 2 points, that is first principal focus and double of it, that is f1 and twice f1. So here we have an object between f1 and twice f1. So we need to find position, size and nature of the image. So again we will use the two rules, the two incident rays that we take. The first incident ray, as you can see, is parallel with the principal axis, and the rule says if the incident ray is parallel with the principal axis, then the refracted ray must pass through the second focus. We are using the same rule again and again, so it should not be difficult for you to draw the ray diagrams. So this is the refracted ray which is passing through the second focus. Incident ray parallel with the principal axis, refracted ray passes through the second focus. Now another incident ray that we are taking is passing through the optical center, and the rule says it goes without any deviation. That means it will travel in the same straight line. So as you can see, these two refracted rays intersects at this particular point. So wherever the two refracted rays intersect, just drop a perpendicular on the principal axis. I hope you are finding it easy now. So this will be the image of the object which is kept between f1 and twice of f1. So with rules it's very easy and simple. Now position of the image. As you can see, this image is formed beyond twice of f2 or behind twice of f2. So you can write it is formed beyond twice of f2. Now if you look at the size of the object and the size of the image, it's very clear that the size of the image is greater than the size of the object. That means the size of the image has been enlarged or magnified. So you can write magnified image is formed. Now nature, again, since it is inverted and it is formed due to actual intersection of the refracted rays, we can say it is real and inverted. It's that simple. So just learn the rules. You don't have to mug up anything. The image will be formed at its position if you follow the rules. So this is case number 4. Now let's do case number 5. Alright, so this is case number 5 where our object is given at f1. So we have to place the object exactly at the first focus. So you can see here we have the object at f1. So we need two incident rays. The first ray that we are taking is parallel with the principal axis, and the second ray we are taking is passing through the optical center. So using the same rules again, if the incident ray is parallel with the principal axis, then refracted ray must pass through the second focus. So if you draw the refracted ray, here it should pass through the second focus like this. So incident ray parallel with the principal axis, it must pass through the second focus. Now the second incident ray we are taking is passing to the optical center, and it goes without any deviation in the same straight line. So here in this case we have two refracted rays, but in this case you can see that the two refracted rays are not intersecting each other, rather they are parallel with each other. And whenever the rays are parallel to each other, we have discussed this while doing the mirror also, we will consider that these rays will intersect at infinity. After going through long distance, these two rays will intersect. Alright, so here you can say that the position of the image, it will be formed at infinity, because the parallel rays intersect at infinity. We consider that, so image will also be formed at infinity itself. And since the image is formed at infinity, the size of the image will be highly magnified. A large inverted image will be formed, so it will be highly magnified. And the last case, nature of the image, since we are considering that these two reflected rays will intersect at infinity, so we'll get real and inverted image. So when an object is at f1, image is formed at infinity, it will be highly magnified and it will be real and inverted image. So this is case number 5. Now let's discuss the last case, which is very important also. Alright, so this is the last case for image formation by a convex lens here, where our object is kept between optical center O and the first principal focus f1. So as you can see, we have kept this object between f1 and O. Now here we need two incident rays. So let's draw the incident rays, one parallel with the principal axis and another incident ray passing through the optical center. So remember, we are using the same rule again and again here. So this incident ray, which is parallel with the principal axis, the rule says that after refraction it must pass through the focus, second focus. So this incident ray, after refraction, it must pass through the second focus f2 like this. And the second ray that you can see is passing to the optical center, and the rule says if the incident ray is passing to the optical center, it goes without any deviation. So here these two refracted rays, again they are not intersecting, but these two rays are not parallel as well. So how can we form image in such case? Is simply by producing the refracted rays backwards. We have done similar case for mirror as well. So since these two refracted rays are not parallel, they will not intersect at infinity. So in order to form the image, we will produce these refracted rays backwards. We will pull them backwards or produce them backwards. So let's draw this rays backwards and see where will be the image formed. Remember, we are producing then these refracted rays in the backward direction, right? So similarly, we can pull this refracted ray or produce this ray backward. You just have to produce them in the backward direction or in the opposite direction. So at some point, you will see that the two refracted rays, when produced backwards, they will intersect each other, right? So these refracted rays, when produced backwards, you can see it is intersecting at this particular point. So wherever they intersect, what you have to do? You have to just drop a perpendicular. And this will be the image of the given object. Now I hope you have noted the difference here. In all the other cases, the image was formed on the other side of the object. But this is the only case where image and object lies on the same side, right? And you can see the image is erect. Okay, so this is the only case for a convex lens which forms virtual and erect image. So that's why this case is also important. Now let's write the position of the image. You can write the image is formed on the same side as the object. Now size of the image, it is very clear that the size is magnified, or you can write highly magnified also here. The size is, image size is highly magnified. And nature of the image, this is the only case where the image formed is virtual and it is erect. Alright, so where do we use this? We use this in the magnifying glass. Whenever we see minute object with the magnifying glass, then the image formed will be enlarged and it is on the same side of the object. So it's used to magnify the smaller objects. Okay, so we have discussed about the image formation by a convex lens. For a concave lens, you can do it yourself. Just follow the rules and you can form the image through a concave lens. I don't think that it will be much difficult. You just have to learn the rules and do the image formation by a concave lens. I'd like to end this video here because it will be very lengthy otherwise. Okay, if you have any difficulties, you can just comment. I will just draw the ray diagrams for concave lens also and post it in the I'll make a video, or I will take the make a picture and post it in the YouTube. Okay, please do share, subscribe, and hit the bell icon so that you can get the notification. It's high time now for your preparation, and please do comment and give suggestion for what which topic you want the next video on. Okay, all the best. Do prepare well for your exams, and I'll see you in the next video. Thank you, everyone.